Ladies and gentlemen, this is the last lecture in this unit, and it's about motion represented on graphs and on diagrams. Um, some of this can have some math that supports how to understand what's happening. Um, so you'll see some math interpretations on this graph, and some of them are kind of logic interpretations. So if you're able to understand it both ways, that's great. However, it's really important that you're comfortable with understanding at least one of the ways. So I want you to relax if when you see some of this math, if you get confused. If you're able to understand it the graphical way or the image way, then that's fine too. So I'll kind of be directing you through that as we go through. Um, so here's our first term, constant speed. So you'll make a bookmark for this. Constant speed is when an object changes the same amount of position in the same amount of time. And the unit is meters per second. There's not going to be an equation for this word. A good way to think of constant speed is to kind of think in terms of riding in a car where the driver has set the car on cruise control. What cruise control does is keep the car moving at a steady speed, not speeding up, not slowing down, but staying maybe at that constant 55 miles per hour. So constant speed, moving the same distance in equal amounts of time. Your next vocabulary word is motion diagram, and it's really a diagrammatic tool. It's not really a vocabulary word so much, but you have to be able to recognize it, so we use it as a vocabulary word. A motion diagram has arrows that show motions. So it's described as being a one-dimensional pictorial representation of motion that shows position. So this is an example that we're going to talk about momentarily. However, I don't want you to use this on your bookmark. I want you to use the images on the next slide on your bookmark. We just want to look at this from the point of view of a number line to show the basic ideas of a motion diagram. The motion diagram examples are on the next slide. So if we look at this where we go from A to B and B to C, then that clearly is something that's moving to the right. And those arrows show that it's moving to the right. Then from D to C, that arrow is pointing to the left, so this shows something that's moving toward the left. The short arrows from A to B and B to C indicate that the object is not moving very far, compared with D to C, which moves a long way. One of the keys about motion diagrams is that each arrow shown on a motion diagram represents the same amount of time. So with that in mind, it's easier to understand how the representation from A to B shows something that's moving more slowly than D to C, since A to B only went a little way in the same amount of time it took D to go a much longer distance. All right, so here are some examples that would probably be better for your bookmark. There's 4 here. Some of them show constant speed and some of them do not. So let's start with this first one. We're going to start on the left, and this indicates that the object is moving to the right, and this occurs over 7 seconds. So it moves a little way and then farther and farther and farther. So this object is not moving with a constant speed. Number 2 shows something that begins at the left, moves toward the right, and it changes position equal distances each time. So in 6 seconds, this object moves equal distance in each second. So this one is a constant speed example, number 2. Number 3 is very much like number 1, however, it starts on the right and moves toward the left, and it covers longer distances as the 7 seconds pass. So this one is not a constant velocity either. Number 4 shows something that begins to the right, moves to the left, and it moves only a very small distance in each interval of time or each second. So this one is moving slowly. So the 2 that show a constant speed are the ones that are circled now in red, and the one at the top, since it has longer arrows for each of the time intervals, shows that it's moving faster than the one below. This one below shows it's moving only a short distance for each time interval. So the length of the arrow in a motion diagram indicates how fast the object is going. If the arrow is longer, the object is moving faster. The number of arrows on a motion diagram show how many time intervals are covered. Typically, each arrow is worth 1 second. Okay, shoo, that was a lot of stuff. Pause this if you need to as you make your way through this and finish up your bookmarks. For the motion graphs, some kids get all crazy when they look at motion graphs. Hey, they're not that bad, and we're gonna take them in pieces, and you'll find that you'll do just fine with them if you just kind of relax and look at what they show you. So we'll talk through this one quickly, and then we'll pick it apart on the next couple of slides. So the definition of a motion graph is that it's a two-dimensional pictorial representation of motion that shows position and time. X stands for position. You remember that from our first lesson in this unit, that the variable for position is X. So the up and down axis on this graph is for position, measured in meters. The side-to-side axis on this graph is for time, measured in seconds. I know that's weird compared to math, because in math, Y is the up and down axis and X is the side-to-side axis, but that's not the case in physics. Because in physics, we're not talking about just random X and Y's that don't mean anything. We're talking about variables that have true physical meaning. So we know that on the up and down axis, we're talking about position, which is an X. And we know on the side-to-side axis, we're talking about time, which is T. So that's part of the reason why we have really specific labels in physics, because we label them with the actual physical dimension that we're dealing with. So to quickly go through this, and we'll break it down more slowly on the next couple of slides. When there's a positive slope, when the line on the graph does this, moves upward from left to right, then that indicates that the object is moving toward the right. Then when the line is flat and there's no change in position, this shows something that remains at 4 meters. That means it's stopped. The velocity is 0. Then if the line slopes downward on the graph, then that indicates that the velocity is negative and the object is moving in the negative direction. If the slope is steep, it's moving faster. If the slope is not as steep, then it's moving more slowly. We'll take it apart in little pieces. Okay, let's start with the first chunk of this. So this is kind of the math part that might help some of you understand this. And then I'll show you kind of a quick way without the math. But this ties with what you've already done, so it's very doable. So if we look at this graph, we can pull variables off. We can know that x sub I, the starting position, is 2 meters, because at the beginning of this, at 0 seconds, this reads over to 2, and this axis is position in meters. So I can say x equals 2 meters. So xi equals 2 meters. So that's how I read that off of this graph. The time interval was 1 second. We went from 0 to 1 second in this interval. So t was 1 second. And the final position right here is 4. And that was our x sub f. So x sub f equals 4 meters. We just drop those straight into the displacement equation, and we find out the displacement is a positive 2 meters. So from here to here, the object moved a positive 2 meters. We can then find velocity very easily off of this graph by dropping this displacement we just found, 2 meters, into the top of the equation, putting the time in the bottom, and just dividing 2 meters by 1 second, and we get 2 meters per second. So the velocity during this interval is 2 meters per second. Okay, let's do interval 2. All right, so during interval 2, we have a starting position of 4 meters. That happens from 1 second to 2 seconds, so that's a 1 second period of time that passes. So be careful there. We want to pay attention to how much time passed in this interval. So it was 1 second that passed between 1 and 2 seconds. So that's how we got t equals 1 second. Then the final position, oh holy heck, the final position was still 4 meters. So initial and final position are both 4. So when we drop those into the displacement equation, then 4 minus 4 is 0. And that comes over into the velocity equation. We put a 0 in the numerator of the velocity equation. 0 divided by 1 second is 0. So this just proved to us that during interval 2, this didn't move. It just sat in the same place. So the velocity was 0. It didn't move. It was at rest. That's another way that we talk about something not moving in physics. We'll say that it's at rest. All right, now we're ready for interval 3. During interval 3, the starting position off of the graph again, we look right here. This is the starting position for interval 3. We read over here, so x sub I is 4 meters. Then we have to be a little bit careful for this time interval. So we drop down here and we see this time interval begins at 2 seconds, and the time that passes goes 1, goodness sakes. Sorry about that. So the time that passes goes from 2 seconds to 3 seconds. So that's 1 second, 2 seconds, 3 seconds. The 5 is not shown here. However, because of the way this is scaled, this last position would be 5 seconds. So this happens over 1, 2, 3 seconds. So that's how we got a time interval of 3 seconds. Then if we look at this position right here and read across, then that's 0 meters. So the final position was 0 meters. Displacement is always final position minus initial position. So 0 minus 4 gives us a negative 4 meters. And that makes sense because this is moving in the negative direction. It's moving down towards 0. So we have a negative 4 meters. To find velocity, we just take the negative 4 meter displacement we just found and we divide it by the time that passed, which was 3 seconds, and we got a velocity of negative 1.3 meters per second for that interval. All right. So here's the next thing that we're going to do. This is the way you can do this if you don't want to think of it with quite so much math. So 2 ways we can do this. We can look at it and we can calculate the velocities like we just did. And the one with the greatest absolute value is the fastest. So in this case, so the absolute value of 2 is 2. The absolute value of negative 1.3 is 1.3. So 2 is larger than 1.3, so interval 1 is faster. The other thing we can do is we can see which line is steeper. This line is steeper, so it's faster. The next slide is where I'm going to show you the analysis that isn't quite as mathy. So if you want to use this next way of looking at graphs, here you go. This is what I suggest. So I took the same graph and I said to myself, all right, I have this thing that moves away, and then I have this thing that comes back. And I'm just going to look at it when it moves from its starting position back to that starting position. So in this first little interval of time, over 1 second, this moved 2 meters away. And then during the next, when it came back to the same position, that took 2 seconds. So it moved 2 meters in 1 second to start with, and then it moved 2 meters in 2 seconds. Well, based on that, it's pretty easy to tell that if something moved 2 meters in 1 second, it's going faster than something that went 2 meters in 2 seconds. I hope that helped a little bit. That's just another way of kind of analyzing a graph like this without having to do a whole lot of the math that you saw a few slides back. Okay, so a summary. Our 3 vocabulary words are constant speed, motion diagram, and motion graph. Constant speed is when an object moves the same distance in every second. This can also be called constant velocity if you know the direction that something is moving, but typically we'll call something constant speed. Then motion graphs show the position of objects over equal intervals of time with a little dot to show the location. And when the dots are evenly spaced, then the arrows are the same length and the object moves at constant speed. Motion graphs show position in time for an object, and when the line on that graph is more steep, then you know the object is moving faster. We can use motion graphs to pull a lot of information off and do a lot of math, but I have you do that when it helps you. But if that doesn't help you, then we can use that kind of triangle method that I showed you last. Graphs are your friend. They're really not as hard as you make them out to be if you just slow down and read off of the axis and kind of make some notes, sort of like I did as I went through this and kind of showed you how to make sense of these graphs. So good luck on your next lesson. So you want to go on to finishing your bookmarks for 2C and then starting on some practice.